In this video, we're going to look at sample problems. We're going to do both a sample problem when sigma is known, and like we did with confidence intervals, then we're going to move on to some examples when sigma is unknown. And just like with your confidence intervals that you worked on previously, if sigma is known, we're using a z-table. And when sigma is unknown, we move to our t-table. So let's start with the one mean z-test. Just like with the confidence interval, if we can assume we have a simple random sample, a normal population or a large sample, and we know the population standard deviation, that's what our sigma is, we can move forward with a one mean z-test. So let's take a look at our steps within the context of doing them in a one mean z-test. After you read your problem, you are going to set up your null and your alternative hypothesis. Remember what I said in the last video? This is our known value that is true. We had looked at the one problem, we talked about how many hours a week students spend outside the classroom. We had mu equals 6. Your alternative hypothesis is going to depend on the wording within the problem, which is either going to say it is just different from that, it is less than that, or we believe it is greater than that. And that's going to determine if you do a two-tailed, left-tailed, or right-tailed. You never do all three, it's always one of them. Step 2, this is where you list all your important information. But now we're going to be concentrating on step 3, where we actually compute that test statistic. So let's talk about the z-test statistic. Your test statistic is basically a number that kind of determines, well, how far from the mean is our sample statistic. So it makes sense that the numerator is represented by x bar minus our population mean, because we want to figure out the difference, but we have to figure out that not just the difference, but how many standard deviations, which is why we divide by the standard deviation. And as you recall from what you learned about sampling distributions back, I believe it was in chapter 7, that standard deviation is greatly influenced by the sample size. So that's why our denominator is standard deviation divided by square root of n. If you take a look at your formula sheet and you go to chapter 9, here you have your z-test statistic. This is what you're given, and sigma is known. And there's the formula that we just went over. So whenever you're going through any of these problems, you really need to have this formula sheet out in front of you. After we do that, we've split the steps into whether or not you were going to do a critical value approach or a p-value approach. Remember, on a test, I could dictate which one to use, or I might give you the choice. When we go through the sample problems, I will end up doing both, but you will do one or the other. Your critical value approach, recall, uses the numbers along the number line here to break it up into a rejection and do not reject region. And then wherever your test statistic falls, that determines your rejection or not reject. Your p-value puts your test statistic values here, and that is a big difference. In the critical value approach, it is the critical values that get listed on the number line to break up the regions. There are no regions in the p-value approach. In the p-value approach, it is your test statistic that goes along here, and then that determines these areas which now represent your p-values. Okay, in the critical value approach, those areas were your significance level. So they're two very different approaches. How you draw a conclusion, again, on the critical value approach, you simply put an X. Not reject, it's over here, that's a reject, and so on. In the p-value approach, once we get that area, that p-value, we compare it to alpha. If it's less than or equal to alpha, we reject. If it's greater than alpha, we do not reject. The other thing you want to always remember, your p is between 0 and 1. If you're getting a p-value of 2.3, that is not a p-value. Something went wrong. And then, of course, your last step is to interpret. That's that sentence you're going to write after you draw your conclusion. So let's go through and let's do a problem. Make this a little bit bigger so you can see it. There we go. So hit pause, read the problem. And as you're reading the problem, let's see if you can pick out the important information. What is the value we're testing against? What is our X bar? What is our standard deviation? What is our sample size? So go ahead, hit pause, and figure that out, and then come back. So hopefully you were able to read the problem. You figured out what's going on. And the first thing I now want to do is set up your null hypothesis. So what is that value we are testing against? It is usually quite clearly in this final question, if you weren't sure, because there's a lot of different numbers you're given. You're given an X bar, but remember, the X bar is not our population mean. That is just our sample mean. Usually, you're going to find that right here. So we are testing against this known number that the mean of early onset, the age of early onset dementia is 55. So now, for your alternative, also in this same sentence, this sentence kind of puts everything in here. The sentence that's asking at the 1% significance level, do the data provide sufficient evidence to conclude that the mean age of diagnosis of all people with early onset dementia is less than 55? That's key. That also tells you the type of test you're doing. You are doing a left-tailed test. Less than 55, that's a left-tailed test. So what other information do we have? We have our mean. We have a random sample of 21 people, N is 21. We're doing this at the 1% significance level, so alpha is 0.01. We have an X bar of 52.5. And this is another thing you're going to start to pay attention to, because right now I'm separating them into two sections, but as you do other problems and you take the test, they're all going to be mixed up. What is the standard deviation and which type of standard deviation is it? Is it an S, which is a sample standard deviation, or is it a sigma, which is a population standard deviation? This one very clearly is population standard deviation. So sigma equals 6.8. So this is good. We've identified all the information. Now, I'd like you to hit pause, get your test statistic formula, and see if you can plug in all the information. So hopefully you were able to plug in all the information. And if you don't recall where your test statistic formula is, you can go to your formula sheet. Please get in the habit of using that. Z equals X bar minus mu sub 0 over sigma over square root of n. So X bar is our 52.5. Mu sub 0, remember, is the number that's up here, the 55. 6.8 divided by square root of n, square root of 21. So, I'd like you to hit pause, and one of the most important things to do if you are just watching this video and you are not working out the problems as you're doing it, you're going to have issues when you do go to work these out on your own. So hit pause and go ahead and work it out. So I got negative 1.68, and unless I did something drastically wrong, that is the answer. I will double check it though, just to be sure. I'd really hate to make a mistake on the video, but that looks to be good. Now, I want to take a look at these two approaches. So for step 4, again, I'm going to do it 2 different ways. You would only normally do it one way, but we are going to do it 2 different ways. The first way we are going to do is the critical value approach. So recall, this test statistic is a number that represents kind of like how many standard deviations away from the mean is the sample mean, from the population mean is this particular sample mean. So we're trying to figure out, is it providing enough evidence for us to reject a null hypothesis? So anytime you're going to do a critical value approach, expect to see a picture. If you're not drawing pictures, you're going to end up making mistakes. Draw your picture. Go back to your alternative hypothesis. This is a left-tailed test, so I should see a left-tailed test picture. Remember, when you are doing a critical value approach, it's the critical value that goes and is at that line. If this were a two-tail, you'd have 2 critical values, negative and positive, but this is just a left-tailed, so it's going to be negative. Our significance level for this particular problem is 0.01. It's a left-tailed test, so all I need is negative z of 0.01. You can go to your formula sheet, like we did with confidence intervals. Scroll down. Well, you're not scrolling, but flip down. And do you recall this table we worked on before? Okay, this gives you your common z values. We want z of 0.01 because we had a 1% significance level. So 0.01 is 2.326. That is this critical, that's the value that you're going to use. That's your critical value, that 2.326. And it's negative because it is left-tailed. It's our critical value. That is what's going to separate our rejection region from our do not reject. Remember, the rejection region is always the smaller one. It's where the tails are, from our do not reject region. 0 is always directly in the middle. So now, here's the question. Where does our test statistic fall on this line? Well, this is 0. That's negative 2.3. It's going to fall right here. That is in the do not reject. So step 5, which is simply our conclusion, is do not reject. I want to do now the p-value approach. The p-value approach is a little bit different. Still to draw a picture because you need to see the difference. It's still left-tailed, but here's the big difference. You're not putting the critical value there, you're putting your test statistic down here, which is negative 1.68. And what we want to find is this area. This is no longer our significance level like it was before. This now represents our p-value. All right, so we want the area to the left of negative 1.68. You need to go, because we are doing a z-test, you need to go to your z table, not your t, you got to go to the actual z table. And recall, it was negative 1.68. So go to your z table, find negative 1.68. And it looks like I have a value of 0.0465. An area of 0.0465. So that means my p-value equals 0.0465. Now, in this problem, right, alpha directly under that is 0.01. So you have a p and you write alpha. What is the relationship between p and alpha? 0.04 is definitely greater than 0.01. So we would state p is greater than alpha. Therefore, remember what we said, when p is greater than alpha, do not, sorry about that, reject. So for both of these, there is no way you would do one approach and get one conclusion and the other approach and get a different conclusion. If you happen to do both approaches, you're going to end, if you're not, you have to end up with both conclusions the same. This is a do not reject. What does that mean for step 6? I'm going to put step 6 over here because I'm running out of space. At the 1% significance level, you are basically rewriting this sentence. Okay? You're rewriting this question that's being asked at the end of your problem. At the 1% significance level, in fact, I'm not even going to rewrite it, I'm going to draw it on here. At the 1% significance level, all right, comma, the data, we do not reject. So the data do not provide sufficient evidence. Dot, dot, dot. To conclude that the mean age at diagnosis of all people with early onset is less than 55 years of age. The data do not, that doesn't mean that's not it. It just means your sample, this particular sample of just 21 people, do not provide sufficient evidence. Okay? And then you would finish that sentence with what's on there. So that's how we would do a critical value approach. I'm actually going to turn this video off now, and I'm going to do the when sigma is unknown in a separate video. So I'm going to stop this one right here.